activity. While she's passing, now listen to me. I'll tell you a few things. The next topic is a topic that you may have come across when you were in grade 9. Actually, I'm sure you did, because even if you did your maths prior to Euclidean geometry being put back into the curriculum, in grade 9 they talked about similar shapes and similar triangles. You might have some vague recollections of it if you hadn't done geometry after that. Now, what are similar shapes? Similar. Well, you know about congruent shapes, isn't it? If two shapes are congruent, what does it mean? It means they are identical, right? Everything about them is the same except where you place them. The measures of the angles, the sides, and the area, everything would be identical. If we say they're similar, what do we mean? What? Yes? Yes, Nanda? Yeah, that's in a triangle and quadrilateral, that's true. But in general, in a general sense, what would we mean when we say two things are similar? Generally. It means they look the same, but they're not necessarily of the same size. Isn't it? Yeah. Like if you take a photograph of your size, unless you take it the size that you are, you'd have a small photograph. Isn't it? Now that photograph ought to be similar to the original, of course, unless you distorted it by using some other application that you might have on your camera. But otherwise, it should be similar. So, but we need a mathematical definition. So really speaking, what happens in similar cases, in the case of our rectilinear shapes, our straight line shapes, is that two shapes are similar if one is either an amplification or a magnification or a reduction. In other words, and it has to be proportional. In other words, it mustn't be odd. So, for example, if you took a picture of me and you left it as it is, anybody looking at it should say it's me. Why? Even though the size might be smaller, but it's me. Of course, if you go and mess it up by taking the head and pulling it up and making a cartoon out of me, and by pushing up my forehead and making it extremely big, or taking my chin and making it extremely long, then that won't be similar anymore. Would it? No, it will be a distortion. So, what we're going to do is study triangles, similarity in triangles, and the definition is very simple. Well, for any quadrilateral for that matter, for two quadrilaterals to be similar, all you need is for their sides to be in proportion. You know what that means? If you take one side and choose another and put it over that, you'll get a certain ratio. And if you do that with similar pairs of sides and you get the same ratio every time, then, and, not then, and if the angles in the one quadrilateral or one polygon is the same as in the other, or as equal counterparts in the other, then you will conclude that those two shapes are similar. But in the case of triangles, it's more convenient. In a triangle, if you can show that those triangles are equiangular. Now, this word equiangular poses some problems. Sometimes people don't know what's the meaning of equiangular. What would be the meaning of equiangular? Yes? Equilateral? What's the difference between equilateral and equiangular? What do you know about equilateral triangle? All the sides are equal and all the angles are also equal and they're 60 degrees each. Now when I use the word equiangular, how would I use it? I must talk about what? Two triangles or more, but at least two triangles. So the first thing is equiangularity is a comparative term. You're comparing two different triangles. In other words, you're saying one triangle is equiangular to another triangle. Do we say one triangle is equilateral to another triangle? Do we say such a thing? No, an equilateral triangle is a description of a type of triangle. It's just a type, like isosceles. Whereas equiangular is not a type. It's a comparison between two triangles. The two triangles are equiangular. What does it mean then? Does it mean each of them are 60-degree angles each? Yes or no? No. What does it mean? It means if there is an angle equal to 30 degrees in one triangle, there is an angle equal to 30 degrees in the other. If there is an angle equal to 70 degrees in the one triangle, then there is an angle equal to 70 degrees in the other. And of course it's pretty obvious the remaining ones will be 80 each, isn't it? Yes, because they have to be, because the angles of a triangle add up to 180 degrees. So all you want for equiangularity is that the angles of one triangle must have equal counterparts in the other triangle. You know what that means, isn't it? Each angle must have an equal partner in the other triangle. Okay, that's what it means. So if you can get that, then you say those two triangles are equiangular. And now, if two triangles are equiangular, we can conclude, because that's what the theorem tells us, that the sides will be in proportion. And the meaning of that is very simple. Here, in your activity sheet. Well, the first I've just shown quadrilaterals. In fact, any set of polygons. The way to check out whether they are similar is that we have to show that the angles are equal, in other words, they are equiangular, as well as the sides in proportion. In other words, both are requirements. It's only in the case of triangles we have a very special case where we can prove that if these two triangles are equiangular, then their sides will be in proportion and in the order in which the angles are equal. Now notice there's an x there and there's an x there. Right? Notice an x here and an x there. And a y there and a y there. Now, if you are naming the triangles, you've got to name it in order. Otherwise, we wouldn't be making sense. Because if the line that goes from x to y is AB, then the line that goes here would have to be DE. So it would have to be AB over DE. And then, of course, if we go from y to z, it will be BC over y to z here, EF. And the remaining ones are very easy. AC will be AC over DF. So that order in which we name those that triangle is very, very important. Because it tells us how the ratio goes. Now, I don't know whether it makes no sense to you. If it doesn't, it will make sense just now. All I'm trying to say is this. That if I say that AB over DE is equal to something, I can't make a pick of anything that I like. In other words, I can't say AB over DE is equal to AB over EF. That won't make any sense. I've got to link them to the angles. Can you see? From x to y is AB, and then of course x to y there is DE. So AB over DE, that's one ratio. It's equal to y to z, BC over y to z, EF. So you got the other ratio, and you can equate those. The ratio is always there, but what you can equate is what's your question, right? And then of course you can equate that to AC over DF. And there I've shown it to you. If, that is the fact. If in the triangles ABC and DEF you've got a situation where A is equal to D, B is equal to E, and C is equal to F, then you can conclude the statement here. And this is a marvelous statement. Why? Because it gives you equations. Isn't it? In fact, you've got three equations here. Where are your three equations? That is an equation, isn't it? AB over DE is equal to BC over EF. That is another equation. BC over EF is equal to AC over DF. And then that is another equation. Isn't it? AB over DE is equal to AC over DF. So if you know some of those sides of the triangle, you can tell others. Sometimes all, depending on how many you know. Right? So if with any equation here, you know that, you can find that one. So that's the benefit for us, for the time being. So those triangles are called, so in other words, if we can prove that two triangles are equiangular, then we can conclude that they are similar. And that means that their sides will be in proportion. And that's a statement you arrive at. And that's our plan. So what are you going to do just now for me? You're going to try to show that triangles are similar. Why do you want to show that they are similar? Why? Because you want that statement there. That's why. You see that statement there, AB over DE is equal to BC over EF is equal to AC over DF? That's what you want. And you are not going to get that unless you can prove the two triangles are similar. So, two triangles are equiangular. Equiangular meaning we're going to show that an angle from one triangle has an equal counterpart in the other, and similarly for another pair of angles, the third pair will automatically be equal. Why? Why is it if you can prove that two angles in a triangle have equal partners in the other triangle, then the remaining angles will automatically be equal? Why? Are you listening? Why? Because the remaining what?
Because the sum of the...
That's right. Because the sum of the angles of the triangle will add up to 180, so those will automatically be 180 minus the other two, and it will be the same in both the triangles. So that will be enough. Then I'm going to quickly tell you about the converse. This proof is not particularly hard, actually. It's easy. You can read the book, but I'm not going to give you any hints on it now. The converse of this theorem would be what? That suppose you have this, somebody tells you this, that in these two triangles, AD over PQ is equal to BC over QR is equal to AC over PR, then you can conclude this. You can say, the angles must have been equal. Right? That's what you can conclude. So we've got those two facts, and on the basis of those facts, we want to solve a lot of problems. Right? But I am going to demonstrate, I'm going to have to use a board because I don't want to write here. I'm writing all the wrong things when I write there because I'm looking down and up and I'm missing everything. So what I'm going to show you now is quick ways of proving similar triangles. And I've listed them also. Don't worry, they're all there in that activity. But I want to demonstrate to you, and I want you to be able to very, very quickly absorb it and keep it in your head. So what I'm going to do is I'm going to show you standard cases of similar triangles. In other words, if you've got a triangle like that, now, how to find similar triangles? It's going to be a challenge all the time, finding similar triangles somewhere. How would you find them? Well, as soon as you have a triangle like that ABC, and if you draw a line parallel like that and call that DE, will you have two similar triangles? Yes. Certainly. We will definitely have two similar triangles. How come we'll have two similar triangles? There are only two triangles. Which are the two? Triangle ADE and triangle ABC. Those are the only two. Right? In other words, as soon as you draw a line parallel to one side, you will have two similar triangles. On what basis? In other words, are you saying that all the angles in that triangle will equal all the angles in the big triangle? They'll have equal partners. Yes, they will? On what basis? Well, the A happens to be in the small triangle, and the same A happens to be in the big triangle. So we say that those are common. I've got it listed there. You're going to look at it just now. Maybe I should make you look at it first and then talk about it. I'll just talk about one or two, right? I'll do, and then you can go through the others. So these are two lines that are parallel, and you arrive at that, and you can say, and we use the sign here for similar. What do we use this for? For congruence. We use these sort of three parallel lines to say that they are similar. And immediately, if you wrote it correctly, now how do you know that the angles are equal? That one's common there. That angle there, D1 is equal to B. Why? Because they are corresponding. And so if you have to write the reasons, you will say A is common, D1 is equal to B because they are corresponding angles, and DE is parallel to BC. And the remaining angles you can say are equal anyway because they will be, or you can use corresponding angles for that too, and you'll make such a conclusion, and then you're going to check whether your labeling is correct. From A you went to D, so from A you can go to B because angle B is equal to the angle at D. And so you got it named correctly, so the remaining one's got to be right. And immediately after that you can write a proportionality statement. In other words, we want to write this kind of a statement. Now, there are very convenient ways to write that. Because if you label correctly, you can just take them like this. Actually, you take them in many ways. But we can take AD and pair it up with something here. It should be the same as, I should go with that. AD over AB would equal to, and then we can take that and put it over that in the same order, DE over BC. And that should equal, and then of course the remaining thing would be the AE and the AC. And so you got your statement. Of course you can get it a few other ways. You can even, as long as you keep the order right, AD over DE can equal to AB over BC. There's various ways that you can prove all of that. But if you keep to any one standard way and say take them pair at a time, say AD, AB here, DE, BC there, and AE and AC over there, you got yourself a statement. Now this is a valuable statement for you every time you have similar triangles. Right? That's a very important statement. Now, here we've got parallel lines. As soon as you see parallel line in a triangle, you've got yourself two. What kind of triangles? Two, what's the word? Similar triangle. Similar triangle. Similar. We use the word similar. So, similar triangles. So I want to give you 6 cases that you must try to recognize everywhere. Now those 6 cases are recorded in your activity. The second one is there and I want you to look it up yourself, right, and read it. I don't know the order in which I got it. And the third, have a look quickly at the second one. Is it following in the order that I'm telling you? Yeah. Yeah. So the second one, how does that look? Just a shape like that. Is it? Right? And so that is PQ and that is RS. Right? And this line here parallel to that line. And as soon as you see that, can you conclude that those two triangles are similar? Why? Because you've got equiangular triangles and there's only 2 of them there, PQT and STR or SRT, whichever way you want to name them. I've named them there as PQT is. PQT and SRT. And how do we know that they are similar? Alternate angles and vertically opposite angles and alternate angles or remaining angles. And so you've got those 2 pairs of triangles parallel, and see I've written the fact down at the bottom. Can you see that? Okay. The next type. Now, why? These are the very standard ones. Why am I worrying about them? Because I want them to stay in your head. Then you'll be able to see them in other places and be able to answer and solve difficult problems. So,
sorry, Patrick, you know what, maybe you stand on that side.
oh,
Sorry.
yeah, no, that's fine. That's fine. Yeah, the next case, right? The next case that I've got there is a circle now suddenly. Then we got a circle. So every time you see a circle, and you see 2 chords intersecting like that, A, B, and C, D, intersecting at some point, what did I call it? Oh. As soon as you see 2 chords intersecting like that, immediately you can tell that those 2 triangles formed will be similar. How come? Well, this one must equal that, isn't it? Why? Because they are vertically opposite. Where's another pair of equal angles? Yes? Angles in the same segment. So this one is X, that one must be X. If this one is Y, that one must be Y. So you've got equal triangles that are equiangular, and immediately you can conclude that triangle AOC, notice the naming, DOB would be similar. Triangle AOC is similar to triangle DOB. Right? And you can immediately write down that statement too. AO over DO is equal to OC over OB is equal to AC over DB. So let's master these 3 cases. I want you to have it in your head. The first case is when you see a line parallel to one side of the triangle, immediately you've got yourself a pair of similar triangles, right? Next, when you see a shape like this, actually the way we describe this is we say a line is drawn parallel to one side of the triangle inside the triangle, and in this case here, we say a line is drawn parallel to one side of the triangle outside the triangle. You know, there's your triangle, and outside you draw a line parallel, and of course you extend it. So this is an external parallel line, and that's an internal parallel line. But really speaking, those two are the same. Isn't it? It's the same, because you've got parallel lines. This one happens to be inside, and the other one will be outside, and you'll have a similar situation. But what's the benefit for you? If you see this anywhere, you know you've got similar triangles. If you see that anywhere, you've got similar triangles. If you see that anywhere, you've got similar triangles. The other case number 4. Here also, you see, if you draw two chords, they may cross each other, or they might not cross each other. Or if they're parallel, they won't cross each other at all. But sometimes if they're not parallel, they won't cross. For example, like this. Now those two are not crossing inside. But if I extend them, will they cross? Yes, because they meet. So if we extend them, then they're bound to meet there. Now we're going to end up with two triangles. The question is, are these triangles going to be similar? Are they going to be similar? How do you know? How do you know? Well, let's name them, right? I like to name them the way I named it here, so you would. A, B, and P here, and D here, and C there. So I've got two triangles already, a small triangle and a big triangle, right? Now I need pairs of equal angles. Well, first of all, you can say P is in the small triangle as well as the big triangle. Is that right? Where's another pair? Yeah? Another pair? Type? Exterior angle of the cyclic quad. Is this a cyclic quad? Is that one a cyclic quad? Yes, and this happens to be the exterior angle. It must equal to the interior opposite. So if that one's X, that's one's X. If that one's Y, then that one's Y. So small triangle is similar to the big triangle. Can you see it? So from here, triangle P, D, D. Notice how I'm going to label them. I'm going to start with P again. Now, I said P, B, D. Can I go P, A, C? Yes or no? Can I go P, A, C? No. Why? Because there's an angle Y here and there's an angle X there. So if I went from the P to the Y, then I must go from P to Y there. You see, it's not like parallel lines now. Are these lines parallel? No, they're not parallel at all. They need not be. So it's P, C, A. And then you can write your proportionality statement. So that is case number 4. So you've got 4 cases and they must remain in your head and you must recognize them anywhere. 5. Case 5. Case 5 is, suppose you have a circle and you have a tangent. Right? And then from the end of that tangent you have what is called a secant, an extended chord. You know, we came across that before, isn't it? An extended chord is called a secant. So if you have a tangent and a secant like that, and how is it labeled? T, P, A, B. Then you have yourself 3 triangles here. 3 triangles if you join all of that. 3 triangles, but in general, only 2 of them will be similar. Which are the 3 triangles? The 3 triangles are, this is A. No, this is T, right? T, and I named one 1 and that one 2. At A, I named that one 2 and that one 1. Okay, so BTA is another triangle and PTB is a third triangle. Two of them are definitely similar. Which one? Well, for a start, for you to do anything at all, you must find a pair of equal angles. Right? Is there another pair of equal angles other than one you might call common? Are there any equal angles in this diagram at all? Forget about triangles. Forget about there being any triangles. Are there any equal angles, and what tells you? What would be the reason? Yeah? Tangent. When somebody says tangent, what comes to mind? Two important facts, last week's facts. What are the two facts about a tangent? A tangent is perpendicular to the radius. And then angle between tangent and chord equals angle in the alternate segment. So this one here is x, and that one there is x, and at least you've got one pair of equal angles. And now you've got a common angle, which means you can take the big triangle and you can take the small triangle, right? Which means the remaining angles will be equal. That one in the small triangle and that big one there in the big triangle. So if you're starting with P, you can go to the X and then go to the A. Then because you started with P and P is common, you have to go P, but this time you'll have to go to the X, which is B, and then just T. So the triangles will be P, T, A is similar to triangle PTA. I went from P to X, so let's go P to X, P, B, T, triangle, and I can write my proportionality statement. This is a very, very useful fact, because if you write the statement down, you'll have PT over PB is equal to TA over BT is equal to PA over PT. That's right, isn't it? And now notice if we take these two. If I take those two there only, and for the time being forget about that, from there I'll get PT squared is equal to PB times PA. You see that? PT squared is equal to PA times PB. Now let's look at it. PT is what? It's a tangent. In other words, if you square the tangent, it's actually equal to the P times the A multiplied by the P times the B. Now very often they ask you to prove this. And they don't ask you to prove similar triangles, so you've got to find the similar triangles. So every time you see a tangent, expect what? Similar triangle. You listening to me? Every time you see a tangent, expect similar triangles. That's the whole point of this. Then, of course, finally, number 6 is a very interesting thing because we can actually use this to prove Pythagoras' theorem. If you have a right angle triangle like that, and if you drop a perpendicular from there, then you've got yourself 3 triangles. And you know what's nice about that? What? Those 3 triangles are similar. So it's going to be your job to prove. Have I shown the proof? No, you're going to do it. You're going to say how come, and you're going to do it just now. A, B, C, D, and you're going to say how come that they are similar. In other words, where are the angles? So that's what you're going to do there. Now the way of writing it, if you have to prove, in other words, assuming you take this small triangle here and the whole big triangle. So say you would say in triangles A, B, C, and you want to take the big triangle and that small triangle there, and you can name it any order here, but as long as after you've done it, you name it correctly. So if I say D, A, B, then I'm going to have to find a pair of equal angles. And I'm going to say Y. and another pair of equal angles, and I must say y. And then I must say that the remaining angles will be equal because of angles of a triangle, or I can list them. Remaining angles are equal. And then I will say, therefore, triangle ABC is similar to, and when I write similar, I must put the correct order. And that's what you're going to do. So, take the first pair. The first pair that you are given is triangle ABC is similar to, and you want to prove it equal to similar to DAB. So we're going to prove it very quickly. And then after that, we've got a whole lot of applications to do, which you will systematically work. These 6 are very, very valuable because every time somebody asks for similar triangles, you must look for one of these first. And if you find them, then you should get happy because they'll always be there. They'll always be there.
Students, if you're thinking about teaching, as Moses said, he's doing the entire grade 12 syllabus in 2 hours here, right? There's no way you're going to do all 6 in one lesson. Hey, but he's giving you an idea that when you teach similar triangles, after you do those theorems, perhaps then you can break this up into 6 different lessons, where you do this first time, and then you do a lot of examples to do with that. You go and look at past year papers, and you look at all the similar examples, maybe the last 2 or something like that, that fall into this, and then that. And then maybe another lesson that deals with this kind of example, until it becomes familiar to the students, and so on. Please, you never do all 6 in one lesson. But it can give you ideas on how you can teach.
You'll be amazed.
They ask you to do it here.
I have seen teachers who want to teach full of geometry in 1 or 2 lessons. You know, they say, no, I'll finish it in no time. Sometimes you ask the teacher, when you start your geometry, no, I will start it just now. No, I only need 2 periods to finish it.
And 1 weekend. And we see PGC, you know, we've been going on to teaching tactics. So now what's happening is people watch all the PGCE students. Because in the PGCE students, they haven't thought about it. So they'll teach a lesson like this. They'll do all of that in 1 lesson. Because they don't think about what is the difficulty in each one, which you probably think about. How do I teach it? What do I need? What can I make simple? So we hope that we won't be seeing this.
You see, with children, they need a lot of repetition. Actually, not only children, even adults. Even as you need to. If I come across something for the first time, it doesn't settle in my mind immediately. I'm going to look at it a few times over. Of course, as you grow up and you have more experience with maths, you might need lesser practice than others. But those who have not had much experience with it, they're going to be repeating it over and over again. You see these diagrams. We might think it's easy to read those diagrams or see them. But for many children, that looks just a mess of lines and circles and curves. Nothing there makes any sense until they keep looking at it over and over, and then they see angles between tangent and the chord. Some children ask them, don't you see equal angles there? No, I didn't see an equal angle. And what's a tangent all about? I don't know. I know you told us about tangent, but I forgot anything else. So things don't come to mind very quickly until you repeated things a lot, many times.
And you repeat the common things. Get them to see some common things. It starts off with repeating the same kind of exercise. Like even if you take the same thing for the slower learners, change the numbers. Start off like that so they can get used to this. This is like a prototype example. Then you move to a different example. Until it becomes a little bit routine, then you can bring in the extra, other issues that are a bit more complicated. Don't do the complicated immediately. Otherwise you chase them away. They all are not going to know maths as well as you, right? Just my concern.
Okay, prove those 3 pairs of similar triangles, and as soon as you've done it, I'll come around and look at it. Then don't wait just to start doing the exercise that's coming up. Right? The one on the
You can give them activity now.
There's still got more to do here.
Okay.
The simple application. If we let it equal y, then we can write y here and y there. So in this small triangle, we got an x and we got a y and we got a 90. This small triangle, x, a y and a 90. In the big triangle, we've got an x, a y and a 90. So all of them must be similar. You get it? And what fact are we using? We are using only one fact. And that fact is that the angles of a triangle are 180 degrees, nothing else. Of course, you were given that one angle is 90, so the remaining one is 90. And that is all. So on that basis, the three triangles will be similar. The challenge is to name it correctly. Right? The naming correctly is what your challenge, because you are going from A to B to C. That means you're starting at the right angle and then you're going to the Y and then you're going to the X. So in the small triangle, you have to go from the 90-degree angle D to the Y, which is D, and then the A. So D, B, A. And similarly for this triangle, you start with D because of the right angle, and then you want to go to Y, and then D, A, and then a C. And then you have those three kinds of similar triangles. Now, notice what's so nice about this. You can use those similar triangles to actually show, to prove the theorem of magnetics. Because if you go to first true, on the basis of the first true, well not the first, the ABC similar to the small one, you can actually prove that AB squared is equal to BD times DC. There I have written it here. AB squared is equal to BC times DC. How do you think you'll get that? When you write your proportionality statement down, when you write that something over something equals something over something, you see AB appearing twice. Why will the AB appear twice? Because AB is in the small triangle as well as in the big triangle. Then the AB squared will equal to that. Then if you take the other small triangle and the big triangle, you'll arrive at AC squared is equal to BC times DC. Can you see that? Now, why would you arrive at it? Because in this small triangle there's an AC and in the big triangle there's an AC. Now notice, how can we prove Pythagoras' theorem? Very easy, just go and add those up. You add AB squared plus AC squared will equal to BC times BD plus BC times DC. And then I just pull out BC as a common factor, and I'll have BD plus DC. I pull out BC as a common factor. And what is BD plus DC? BD plus DC together, what does it make? It makes BC. And so you end up with a BC times BC. And what is BC times BC? BC squared. So what have we really proved? That AB squared plus AC squared is equal to BC squared, and that's a proof of Pythagoras' theorem. Right? Okay. There are a few other things that we can prove some similarity, and there's one particular theorem from grade 10 which I omitted. I don't know, I think I omitted it because there were so many facts here. And that theorem says this, that maybe you should just take a pause now. We haven't covered all of that theorem. I want you to give a few of the last exercise. It's this theorem here, which you can prove by using Pythagoras. Again, I want to take out one of these, right? Right at the end. I actually like to leave these here because you see, it's so nice to have this on a page and keep it in front of you every time you have problems with similar triangles. I'll tell you what's the advantage. When you're looking at a complicated diagram and they ask you to prove two triangles similar, look which one of these will feature. And you'll always notice that at least one of the features, if it doesn't, then obviously it's a much harder problem. But usually these are the kind of things that feature. Or information is too easy to give. It's either too easy or too difficult. We don't get any of these. The too easy will be everything is given in the diagram. In other words, angles are all, the pairs of equal angles are shown already. Or it's extremely hard. But that is not very, very frequent. There is another theorem that you do in grade 10. A very useful theorem. And most people forget it. Say if you have a triangle ABC, and if you take the middle midpoint there, a midpoint here, and I draw a line there. I just took the middle. The midpoint there, and I draw. The theorem actually says that a line that joins the midpoints of two sides of a triangle will be parallel to the side here. But you can prove that. How can you prove it? Because if this is a midpoint, what is the ratio of that over there? This is the middle. So if I put B there, and I put E there, what will AD over DB be? AD over DB. What? Yeah, well, what is the answer? Is there an answer AD over DB? They are equal. The answer must be 1. Isn't it? The answer must be 1. How do you know it's 1? Because you're taking the same distance and putting it over the same distance. It will just cancel out. If this was 5, then that's supposed to be 5. Why? Because you took the middle. Did you take the middle? You took the midpoint. So if you take the midpoint, then whatever that is, that must be the same. So AD over DB must be equal to 1. Because AD is equal to DB. And similarly, AE over EC, although they are not equal, but the ratio will still be 1. In other words, AE over EC would be, those two are equal, so it become 1. Now, we learned the theorem, the converse of our first theorem, of the very first theorem we did today. That if AD over DB is equal to AE over EC, then this line here must be, isn't it? So we wrote it by another method. If you did it in grade 10, then you will have to use parallelograms. But there is another fact that comes up, which comes up on account of similar triangles. And the similar triangles will be able to actually, will enable you to prove that DE is equal to half of BC. And this is a very useful fact to remember. That if you got the middle, you see, the theorem that you have done is a general theorem. In other words, if you drew a line parallel to BC, any line parallel could be there. Then it will divide the other two sides in proportion. Right? Proportionally. That's a general theorem. But this one divides it right in the middle. Then that theorem must hold. In other words, that over that must equal to that over that. And of course, if we can prove these two triangles similar, which we now know from that case there, then we can actually prove that DE is equal to half of BC on the basis of similarity. But in grade 10, the grade 10 children would not have done it by that method at all because they didn't know about similar triangles. Then you think you know what method they use to prove that that is parallel to that equal to half. Well, they use the knowledge of parallelograms. I'll have you do it even if you don't follow it, but I know those of you are interested. Well, you just make a little construction like that in such a way that that part over there. Right. Anyway.
You take a blanket and put it there.
No, on screen.
Take some blanket.
Thank you. Yeah, so yeah, so there you have this triangle here. Can you see what I'm saying? Yes. Like that. A, B, C, midpoint. Right? D, midpoint. E, and that part is equal to that part. And we want to prove what? We want to prove two things. One, we want to prove that DE is parallel to DC. And then two, we want to prove that DE is equal to half. Okay? Let's see. Now you can see. So we will prove two things. One, that DE is parallel to BC, and we will prove that DE is equal to half of BC. Now, how will the children in grade 10 do it? Well, all they do is extend this. And you'll see all these things. I've got a set of problems that are coming up in activity 3. So all these sorts of facts come up, and it comes up all the time. So it's nice to know it. So you make a construction like that in such a way that you make that part equal to that part. Now all you're doing is that's a very, very simple construction to make. In other words, you say, I will take D and I'll extend it. How far am I going to extend it? I'll stop it where it equals DE. That's all. I'm just going to extend the line and I'm going to stop it where it's and I'll call that one D. So now I can claim that D, I'm not claiming, I'm actually setting it up for those to be equal. Now when you see a picture like this, here you've got this thing equal to that, and that part equal to that. If you just look at it like that, and if you knew all your grade 10 theories, immediately something will come to mind. And what will that something mean? These look like what that are bisecting each other. They look like diagonals of some shape bisecting each other, and there's some shape is not even there. Isn't it? Don't they look like that? Yeah, they look like diagonals of some shape that are bisecting each other. What does it make you believe? That if I had to join that up, what should I have? What should I have? If I had to join them, what should I have? Parallelogram, because only in a parallelogram will the diagonals bisect each other. You see, there's a diagonal going through the middle of that, and there's another diagonal going through the middle. So if I join all of that, I'll end up with a parallelogram. You see, because you've got 5 ways of proving a quad to be a palm, isn't that so? By definition, in other words, the opposite sides are parallel, the opposite angles are equal, the opposite sides are equal. If a single pair of opposite sides are both parallel and equal, and if the diagonals bisect each other, when you one of those cases are not. The other cases, the diagonals bisect each other. So if I have to draw this, that must be a parallelogram. And if it is a parallelogram, then that means this side here must equal that side. Why? It is a parallelogram because the opposite sides are equal, so I can put that in there. It also means that the opposite sides are parallel. It's a parallelogram because the opposite sides must be parallel, so that one's parallel to that. So that means this shape here is a parallelogram. And if this shape here now becomes a parallelogram, why is this shape a parallelogram? Because we've got a single pair of opposite sides, both parallel and equal. Equal came from there, from here to there to there. And parallel came because this is a parallelogram, it has the same line, so that must be parallel to that. And so I've got a parallelogram, another parallelogram. And if I've got the other parallelogram, then it means that DE must be parallel to BC, so that gets ticked. How do I do the half part? The half part is very easy. What's the half part? DE, what's it? That was E, sorry. DF must be equal to BC. Is it so? But DF is 2 times DE. Isn't 2 DEs makes DF? Yeah. So 2 DEs make DF, and DF happens to be equal to BC. Why is DF equal to BC? Because I've just shown this thing here to be a parallelogram. And that means DE would have to be the integral half of BC. Right? So that's all the grade 10s, but you can do that now. I'm not going to do that with you, but it's much easier to do it using similar triangles. The whole thing, because you know the ratio of the two sides is going to be 1 or 1/2. In other words, as soon as you've got similar triangles, then you will say that that part over the whole part is 1/1. 1/2. Because this is AD and that's 2AD. See it? Don't see it? If I say AD over AB, wouldn't I get 1/2? Would I get that? I'll get 1/2. Ah. Similarly, if I take AE over AC, I will get 1/2. If I take DE over BC, I must get 1/2 because the triangles are similar. And so I improve the half. Using the ratio theorem, I prove parallel lines, and using the similar triangles, I'll prove the half. Which you can do with ease. If you wouldn't do that, then you wouldn't solve any of the other problems. So you can work those out. Now what I want you to do, is there anything you wanted to talk about those exercises that we last had? Which one? Anyone? And then I have to demonstrate something to you in the last, in here, was there anything you wanted to talk about? Anyone? Or more? Because we're running out of time, and I want to do something in the last activity. Are all these easy? Easy? Everything in the sheet here easy? All happy with it? Okay. So when we give out the last activity, I want to clear some of those. Because I just want to demonstrate this one or two problems. because the whole thing is 8. Isn't it? Yeah. Now comes the next part. The next part is the part that I want you to watch very carefully. Prove that Ts over Qr is equal to Pt over Pr. Now, as soon as you look at that diagram, something should have struck you in the first place. What did? What should have struck you in the first place? Which picture from all of these over here? Which of the 6 pictures would come to mind? 1, 2, 3, 4, 5, or 6? 4? 4. So that means you're going to get similar triangle. Isn't it? Yeah. 4 is coming there. Right 4 right there. You see? I can demonstrate it to you. 4 is featuring. See? There you go. Can you see the picture? I just took out those 2 lines, and what have you got? Something looking exactly like number 4, which means you've got 2 similar triangles. But you can prove them similar on what basis? That angle T3 is equal to angle R. Isn't it? What's the reason? Why is T3 equal to R? Exterior angle of the side equal. That one is common. The many angles equal, and therefore the 2 triangles are similar, and you'll be able to get out number 1. So quickly do number 2. I'll demonstrate that to you as well, and that will sort of get us to the end of the day. The tangent. And whenever there's tangent, what do you think about? What? Tangent perpendicular to radius, angle between tangent and chord. And if there is anything that talks about similar triangles, then what would you think about? What? That picture there, which one? Number 1, 2, 3, 4, or 5, or 6? Which one? 5. Yes, 5. Now, if it's 5, then where is that 5 featuring here? Let's look at this thing here. I can show you in GeoGebra. Let's see how we're going to get the 5 in this thing here. Well, there it is, right? TA is a tangent to the small circle, so let me knock out the big circle for a start. And just give it a look. And then all these other things here are no use. Let's take it off. Because I want the TA, which is the tangent. Right? What did I want to do? Is there another tangent? No, I don't think I bring the right. Is there another tangent in this diagram? TA is the tangent to the smaller circle. I want to prove that TB, in terms of AD and AD. So which facts must I use? Well, I do see a tangent. But what's my problem with this tangent? I have a serious problem. I can't use any of those 6 there, so I'm going to find another way out. And the other way out, the reason I can't find any of the 6 is because I have a tangent, but from T I don't have a secant. You see? So automatically I know I'm out, even though I remove that other circle so quickly, but I can't have this shape at all coming up because when I've got a tangent, I must have from here another line that will go right across and cut the circle. And I don't have that. Can you see? I don't have it. So either I draw that, which of course would not be necessary in this problem at all, so I can set it up that way and generally it isn't, or that fact is not going to feature. So we read on, is there anything else that's mentioned here? T is the tangent to the smaller circle and the corner of the larger. OD is perpendicular to TD, the line through DNA and cuts circles, so I don't know that there is another tangent. So I don't know that TD is a tangent. And I want to show that I want to write TB in terms of DE and AD. And I don't think I'm going to be able to do that. I think I have this problem. I should have written somewhere that T. If this part is equal to that, and that part is equal to that, what shape comes out? Parallelogram. And if this is a parallelogram, then the opposite sides must be equal. And you got the answer to the last question. Read the last question. What does it say? Prove that. Prove that. ET is equal to BF. Now you never would have seen that if you didn't realize that this is a parallelogram. Isn't it? Yeah, you would not. If you see it's a parallelogram, because the link is so far away. You probably might not struggle in a way that you struggle, but it's not an easy link until you see that that particular shape is a parallelogram. But of course that's quite a problem. So somewhere I should have written to sort of fill it in that TB is a tangent, but I think I'll have to rethink that problem now. But it doesn't matter. I want to illustrate a very nice property of parallelograms in a difficult problem like this, but everything goes haywire and you don't get somebody to visit it again. Alright? No, but that's it. It's one of them. So that's it. Time's almost up. Now, the thing, any questions about it? Any questions? Yeah. TB squared is equal to 480 times PE. Oh, I didn't do that. Oh, that one comes from the. Okay, I wrote it here. I wrote it here. This you know came. This came from the similar time. Then from here I took TD times DB, this part. I took this. And I got TD times DB is equal to FD times DA. That's fine. Then I've got, instead of TD, where is my diagram? The diagram is there. Instead of the TD, I put half TB. Can I do that? So instead of the TD, I put half TB. TD, half TD. In place of the DB, I also put half TD. DB, half TD. Can you see it? So now I've got half TB times half TB is equal to FD times AD. Half TB times half TB is quarter TB squared. Half times half is quarter, TB times TB is TB squared is equal to FD times AD, and therefore TB squared is 4 times FD times AD, and that's what was required. Isn't that what's required? What's working? Oh, the second one. Oh. Oh, it's not the same. Oh, sorry. But that's what I want to prove, isn't it? What's required to be proved? TB squared is equal to 4FD times AD. Oh, that's what I told you. Yeah, I didn't tell you it's tangent. Oh, sorry. But anyway, I'll rework this. I'll probably send it to you. It's quickly make sure it actually works out right. Because if it is often all right, now that actually finishes 3 years of geometry, grade 10, 11, and 12. There is no way that anybody on the basis of 4 2-hour lectures or 2.5-hour lectures can master all that amount of geometry. It is impossible. So, unless of course you spend a lot of time working on many problems, it is possible. But then you must spend a lot of time solving a lot of problems. And that's all that's left for you to do. What's left for you to do is solve a lot of problems. And then in the end you must be able to prove the theorem, because you're going to prove But the reason I didn't dwell on it is I want you to be able to solve problems by applying the theory, because the theory proves all of them, and you can very easily solve it yourself or study it up from a book. So, your job is to go and master these as best you can. And I think next week you're going to do an assessment, but I'll do an overview of everything, we'll summarize it all, get the facts, and show you some things about how we need to teach things to students, and then I'll touch you about your system. Thanks for running through.